Alright, so give you a little bit more context and why do we use limits, why are they useful. So in general, so far we've looked at limits in this form pretty much, which means that we would have said something like as x approaches 2. Well, you can really only approach x from two directions, and we've definitely used this so far, and that would be you can approach it from the left. That would be the left limit. That would be denoted with like this would have been written with the limit of x going to 2 with a little negative sign. That means, you know, if this is 2, start just to the left of it on the number line and start looking at numbers closer and closer to 2. Then hopefully the right limit makes sense then, that if we're looking at the limit for x going to 2 from the right side, that you start just to the right of 2 and get closer and closer to it, and then we get a value hopefully, or sometimes you don't, but generally speaking, at least for left and right limits, you do get values. And then the trick that we've done so far is to compare the left value to the right value, and if they match, we said that the limit existed. Right? That's basically this story over here. We've done this before, right? Graphically. We said, hey, here's a graph, take a look at it, see if the limit exists. And so far we've always said, and that's not going to change, that if I come from the left and I get to a point, and if I come from the right and I head towards a point, is what I should say, and these 2 points match, so if the left and the right limit match, then the limit exists. But in a situation like this, when I come from the left, I end up over here, and when I come from the right, I end up over here. Since left and right do not match, so the left limit is not equal to the right limit, then we say that the limit does not exist. If the limit exists, then not only can we say that it does work, but you can also say, this seems sort of redundant, but that means that the limit is the value that we received when we looked at the limit coming from the left and when we looked at the limit coming from the right. Okay, so that's basically review. Hopefully none of that was very new. So let's look at graphing one of these, and this again sort of basically should be review, and let's see what happens. So lost my marker. There we go. So if I put this on a coordinate grid, and these hopefully are straightforward, pun intended, because they're all straight lines. X greater than 1, so here's 1. If I'm greater than 1, that means that at 1 I should be 2, and then after that I move at a pace of 1 up, 1 over. So that would be x greater than 1. Made a typo here. Let's make this less than 1. Otherwise I have two greater than 1s. Okay, here it says that the function is 0 when x is at 1. So at 1 we're going to put a dot at 0, and then we're going to use x minus 3 if x is less than 1. So at x minus 3 you would be at a negative 2, and then you'd be moving this way, so this again would be an open circle, and then you end up with this picture. So what is the left, or sorry, which limit is this? The x from, and then the 1 and the plus, this is the? That would be the right limit, correct? Because we need to be just past 1. So just to the right of 1, we would be on this one over here, correct? Alright, let me use a different color for that one. So this is the right side. So that limit is what? 2. We are approaching 2. Alright, so the next one would be this one, then would be the left limit, correct? Alright, and for the left limit, what do we get? We end up at a negative 2. So what do we say then about the limit as x approaches 1? Is what? No. It's undefined. Because the left limit, I'm going to change the order I guess a little bit. The left limit does not equal the right limit. You are still thinking about what is the actual value at 1. So the left limit is not the right limit. That's why it's undefined. So the limit does not consider the f1 value that we have. Does that make sense? Because we do know that at f1 this function is worth 0. But the limit is trying to ask you, well, what values are you approaching coming from the left and coming from the right? Well, we're not approaching 0, we're approaching 2 and negative 2. That f1 is just what the value is at 1 for the function. So they don't, I mean, they have something to do with each other, but not necessarily. So that leads us to a whole bunch of situations. So what is the role of the value of a function at c? So this is trying to get back then at, so what is the role of f1? So it is important to the function, so but what does it do in terms of limits and all that kind of stuff? So I have I think 5 or 6 situations here, and they're all slightly different. So here you can see that the left limit is the right limit. So the limit exists. Correct? And not only does the limit exist, the value that we have is indeed the function's value at c. Does that make sense? The function is worth this much. The left limit goes towards that point. The right limit goes towards that value, I should say. And so all three match here. Okay, we could have a situation like this. The left limit is going to equal the right limit, so the limit does exist. However, the limit is not f of c. fc is, in this case, just below it. Okay, so even though the limit exists, it's not equal to what the function is worth at c. Well, here we just take c out basically completely. The limit on the left and on the right equals this value. So the left and the right limit are equal. The limit does exist. F of c isn't defined, but the limits on the left and the right meet, so we do have a limit here. This is the situation that I just showed you in the example with the straight lines. This is the left limit does not equal the right limit. Since the limits don't equal each other, we don't have a limit. fc, however, is defined, so we do have a function value at c. So the next one is take that f of c out again. So left limit does not equal the right limit. There isn't an fc, so no limit, no function value at c. And then this is sort of a strange one, and this is the first time we've seen it, I think. I don't remember what I assigned exactly in the homework anymore, so you may have seen it in the homework, but the left limit does exist. The right limit exists. The left limit equals the function at c. However, because left is not equal to right, the limit still doesn't exist. Even though f of c is defined, and not only is it defined, fc is defined, and it equals the left limit. So that's somewhat unique. So what it does then is that it leads to a formal definition of what it means for a function to be continuous. Okay, so and there are three things that have to happen. The function has to be defined at that point. Okay, so this one over here, this function clearly cannot be continuous. No, this is not continuous, because f of c is undefined. Right now, this could still be continuous. Could be. Once we know that at C it's defined, then we need to make sure that the left limit is equal to the value at C. So right now, this is satisfied both 1 and 2. C is defined, and the left limit is that value. This one breaks down based on this third one over here. The limit from the right is not equal to f of C. So because of this third one over here, which is this little mess over here, this is not continuous. Okay, and it's pretty easy to see on a graph if something's continuous or not. But for a function to be considered continuous, a formal way of looking at that would be to say, 1, it has to be defined, 2, the left limit has to equal the defined value, the right limit has to equal the defined value, therefore the limit of the function at C is going to be f of C. So out of these pictures, which one of these shows a continuous function? The first one's continuous because it meets all three of the parts, right? Why is this one not continuous? Right, FC, even though it's defined, it's not equal to the left and the right limit. Okay, so not continuous. How about this one? This one breaks down immediately. Why? No C. It's not continuous because of f of C not being defined. And how about this one here? Yeah, this one this one messes up on all sorts of fronts, right? I mean, it does have C, but the left limit doesn't equal the right limit, and neither one of those limits even equals C, so it misses on a whole bunch of fronts. Okay, so graphically speaking, it's pretty easy to see if the limit is defined or not. We have a formal definition for it because you don't always have a graph, and the graph, as you know, sometimes is a challenge. Graphing a rational function can be very challenging, for example. Okay? Alright, so determine the numbers at which the rational function is continuous. What do you do? What do I do for A? Factor it. So what can we say? This function is continuous except where? Where is it not continuous? Plus or minus 2. Okay? Use limits to analyze the graph near discontinuities. Sorry. So that means this. And we'll go look at a negative 2 first. I want to know what the limit is for x of negative 2. Sorry, I completely... Yeah. Got another mistake in here. Make that a 2. So the top one should also have a 2. So we can cancel that. That means we had what? What did we have? We had a whole. And the value here would be? What is the limit as x approaches a negative 2 for 1 over x minus 2? Okay. So then we can say, since the function is undefined at x is a negative 2, however the limit exists, that means you have a whole at negative 2, negative 1 over 4. So this would be a formal way of finding those holes and being able to come up with the exact location, which is one of the things that when we did this a while back, a bunch of you lost credit for that, like for example on your final. You didn't give me the location of the hole. You need to be able to tell me what the location of the hole is exactly. It's also undefined at a positive 2. So this would be the limit of x going to a positive 2. And we have a problem here, don't we? I'm already going to use the canceled version of this. So right now I have a problem because can you just plug this in? Yes? No? Okay. So I'm going to have to split this, or I'm going to split this right now, and I'm going to see what happens when I do this with numbers that are slightly less than 2 and then slightly more than 2. Alright, if I have a number that is slightly less than 2, and we'll start with 1.9, what do you get out of the bottom of the fraction? A positive or a negative? If I use 1.9, which is close to 2 but slightly below it, right? And I plug this in here, what do I get? 1.9 minus 2 is a positive or a negative? Negative. So what I end up with here is a negative small number, like negative 0.000001. What do you get when you divide 1 by a small negative number? Huh? A very large negative number, right? This limit goes to negative infinity. What happens when I approach 2 from just above it? I will be at, alright, at 2.1, what happens? I would end up with 1 over a very small positive number. Yes? So where does this go to? Positive infinity. Do you notice that the left limit and the right limit do not match? Yes? So the limit does not exist. You know what? I'm going to say no limit. It's shorter. What does that mean then? What do you have at 2? So what do you get at x is 2? You have what? What kind? You have a vertical asymptote. Because on one side it goes to negative and on the other side it goes to positive infinity. You have a vertical asymptote. Which means that I'm ready to graph this basically I'm ready to graph this function. You should know this has a horizontal asymptote, right? Because the degree in the top is 1 smaller than the bottom, so this is going to go to 0. So you know that at a negative 2 you have what? At a negative 2 you're at a negative 1 over 4, so you have a hole over here. The y-intercept is easy to find, just do 1 over a negative 2. It's a negative half, that's a real point. And at 2, what do you get? Vertical asymptote? There's the graph. Okay, so this is graphing a rational function based on asymptotes. Based on limits. Okay, the last slide just shows you a summary of all the things that you should know about the functions that we've discussed this year. For example, we know, or you should know, that a polynomial function has no domain issues, which means it's continuous across its domain. A rational function, like what I just showed, is continuous except where r is undefined, except where the function in the bottom has a 0. So that could be a whole or an asymptote. Exponential functions, no, continuous at every number in the domain. Okay, and the domain is unlimited. Logarithmic functions, remember, we can only use positives because of the inverse of the they're inverse to the exponential. But on its domain it's continuous, and the same for the sine and the cosine. And then the tangents, the secants, they have asymptotes at pi over 2 multiples, and cotangents and cosecants have asymptotes at multiples of pi because of their connection to sines and cosines. And when is the sine 0, when is the cosine 0. And for the tangent and the secant, it basically works sort of the same way. When's the sine and when's the cosine 0, that determines your asymptotes. So that there's nothing new on there, but it's trying to put it in context with continuity or not continuous functions. Okay.